our modern mechanical systems, everything from giant wind turbines to tiny robotic arms, they're constantly generating this absolute flood of data. We're talking vibration, temperature, torque. So how do we possibly turn all of that noise into something useful, an actual engineering insight? Well, the answer lies in two really powerful machine learning toolkits: classification and regression.
Think about it this way. Your machines are constantly talking. Every single hum, every vibration, every little temperature spike, that's a message. The real question is, are you listening? Today, we're going to learn the language they speak.
So the challenge we have today isn't a lack of data. It's that we're practically drowning in it. I mean, systems like gas turbines and CNC machines are just covered in sensors. They're creating this real-time digital replica of the machine's physical state, what we call a digital twin. Our job is to translate all those raw signals into knowledge we can actually act on. And we're working with all kinds of data here, not just one thing. We're looking at complex vibration signals and trying to correlate them with subtle temperature changes, or maybe torque readings with weird acoustic sounds. Each one of these is a different piece of the puzzle, and machine learning is the tool that helps us put it all together. When we apply machine learning in engineering, we're usually trying to do one of two things. First, we want to understand what's happening right now. That's diagnosis. And second, we want to predict what's going to happen in the future. That's prognosis. These two ideas, diagnosis and prognosis, are really the foundation of intelligent maintenance and optimization. And this slide really breaks it down perfectly. Classification algorithms, they answer the "what is it" question. Is the machine healthy? Is that a bearing fault or a misalignment? It's all about categorizing the current state. Regression, on the other hand, that's what answers the how much or when questions. Like, how many hours of useful life does this component have left? It predicts a continuous number. Okay, so let's start with diagnosis and open up our classification toolkit. These are the algorithms that act like a seasoned expert engineer, sorting through mountains of data to identify and label exactly what's going on inside a system. First up is the decision tree. And this one is super intuitive because it works almost exactly like an engineer's thought process. It just asks a series of if-then questions based on the data. If the vibration is above a certain level, then we'll check the temperature. If that's also high, boom, you've probably found your fault. It's a simple, powerful, and really easy to understand diagnostic flowchart. Here's a perfect example. The algorithm checks kurtosis, which is just a fancy way of measuring how spiky a vibration signal is. If that number is greater than 4.0, it immediately classifies the condition as a faulty bearing. Done. If not, it moves down the tree to check the next thing, the vibration RMS. It's a really clear rule-based path from data to diagnosis that you can easily explain to your maintenance team. Now, a single decision tree is great, but it can sometimes get misled by noisy sensor data. The solution? A random forest. Instead of relying on just one tree, we build hundreds of them, and each one looks at a slightly different piece of the data. Then they all vote on the final answer. So you trade a little bit of that simplicity for a massive boost in accuracy and resiliency, which is absolutely critical for complex systems like gearboxes. Next up, we have the support vector machine, or SVM. So imagine plotting all your sensor data on a graph. An SVM doesn't just draw a random line to separate different fault categories. It finds the best possible line, the one that creates the widest, safest margin between the groups. This makes it exceptionally good at telling the difference between faults that have very similar data signatures. For instance, telling the difference between a motor imbalance and a misalignment can be really tricky because their vibration patterns can look a lot alike. An SVM, using features like RMS and spectral energy, can find that perfect dividing line to give you a high-precision classification. It's a great example of when you need a more powerful model because your fault signals aren't separated by simple rules. Okay, so that was diagnosis. Now let's shift gears and talk about prognosis with our regression toolkit. Here, we're not just trying to identify a state. We're trying to predict a future value. We're forecasting trends, degradation, and one of the most important metrics in all of maintenance, remaining useful life. Remember how great SVMs were for classification? Well, check this out. Support vector regression, or SVR, adapts that same core idea for prediction. Instead of finding a line that separates classes, it finds the best possible curve that fits the data points, all within a certain tolerance. It's perfect for modeling that nonlinear wear and tear over time. And this is where it gets really, really powerful. By feeding an SVR model the vibration and temperature history of a bearing, it can actually learn the degradation pattern and predict a specific number. Not just, hey, it's going to fail soon, but it has approximately 45.5 hours of life remaining. Now that is a total game changer for maintenance planning.
Just like we had decision trees for classification, we have regression trees for prediction. The structure is pretty much the same. It's a flow chart of decisions based on your input data. But the key difference is what you find at the end. Instead of a category like faulty, the final leaf node gives you a number.
Take CNC machining, for example. A regression tree can take inputs like spindle speed and feed rate and predict the resulting surface finish with incredible accuracy. This allows for real-time process optimization. You can ensure quality without needing to stop and measure every single part. You're basically predicting the outcome before it even happens. So we've seen these two toolkits, classification and regression, but how do they actually come together to create these intelligent, self-aware systems of the future? Well, it's all about building a workflow that transforms that raw data into a smart, automated decision. It all starts with sensors collecting those raw signals. Then we extract the meaningful features, things like RMS and kurtosis. Step 3 is where the magic happens. Our machine learning model, whether it's a classifier or a regressor, analyzes those features. And finally, its output directly informs a decision: schedule maintenance, order a replacement part, or adjust these process parameters. And the impact of this workflow is just massive. It's revolutionizing all these key areas. For predictive maintenance, it means we can catch failures before they happen. In process optimization, it's about fine-tuning manufacturing for better quality and less waste. It helps improve energy efficiency in real time and can even monitor the health of entire structures, like bridges and wind turbines. So the key takeaway is really this. The fusion of artificial intelligence and core mechanical engineering principles is creating smarter, more efficient, and more reliable machines. And this isn't just some theoretical concept. This is the engine that is literally driving Industry 4.0. And that brings us to the final thought. As engineers and as problem solvers, these tools are now in our hands. So look around at the systems you work with every single day. Which one of them is talking, just waiting for someone like you to finally listen? Which machine in your world needs to get smarter?